Another detail that is to be discussed is about the input layer itself. Now note that in the input layer, the transformer has no way to discern the sequential ordering in the given input sequence, right? Because they're all treated as vectors. There is no information that is being fed into the architecture that would preserve the ordering or the precedence of each of the given token in the input. Now, to ensure that the sequential ordering is preserved, an additional fixed temporal embedding vector is added to the input. An additional fixed temporal embedding vector is added to the input. So this is also known as the positional embedding or positional encoding, as it is called. Positional encoding or embedding. So I've already discussed this in the context of diffusion models, right, where we gave this temporal information as an input to the underlying unit. So similar idea is followed here. There are multiple ways to incorporate the positional encoding or embedding. One famous way to do it, what is called as the sinusoidal embedding or encoding. It is defined as follows. For suppose J denotes the position in the sequence in the input sequence, and I denotes the embedding dimension. Then positional encoding or embedding defined at j comma 2I is given as sine of j divided by some large number. Let's say that it is 10,000 to the power of 2I comma dm, where dm is the model dimension. This is for the even indices. For the odd dimensions, this is at 2I plus 1. We make this to be cosine of this is j divided by that large number again, 10,000. So 2I comma dm. So this is the definition. Note that this PE would give you a vector of dimensions dm. So let me write it down. So this PE would be in R capital T comma dm. So this should be exactly as the in the same dimensions as that of x, right? Because we need to add it. So what is done is that finally the input x is added with these or let's say input at T or J. So input at position J is replaced by the input at position J and the corresponding positional embedding at J, right? So both of these are in now R DMs in the DM dimension. So now you do it at all J's, right? For all J that is in this particular set. So we have 1 2 up to capital T as the number of tokens that is. So this is, so now this will ensure that the input to the transformer also has the information about the time. So now note that this PE of J is a unique fixed vector that will symbolize what is the corresponding position of a given X given token in the input sequence, right? Because this is a fixed constant, these things are fixed constant for a given J. Therefore this will tell you this will tell the architecture what is the corresponding position that I am looking at, right? So now if I put all of these together and write it as an architecture, so the final transformer architecture, the final transformer architecture would look something like this. So we'll start with uh, input embeddings. These are input embeddings. Now from, okay, let's say that we have X that is given as input. So now this X is typically a one hot vector. So what is done is the you learn an embedding matrix. You put an embedding matrix that is learnable, that will give the input embeddings. Once we have the input embeddings, you take the input embeddings and add it with the positional encoding that we just discussed. This is, you add it with the positional encoding. Then we have uh, a multi-head attention block. This is a multi-head there is a multi-head attention block. Once we have the multi-head attention, we have a residual layer here. So this is residual plus normalization. The layer normalization, what do? We just take the output of the multi-head attention and then we take the input before the attention and we give it as an input to the addition and the residual block. Okay, so this here, this and this. Okay. So now once this is done, we know that we take the output of this and then have a fully connected layer here. There's a fully connected layer. I think I need more space. There's a fully connected layer, and once it is done, we again have a residual, and as I said, the residual and the normalization layer is applied both after the fully connected layer and multi-head attention. This is again the residual plus the normalization layer. This will take the input from the fully connected layer and also the vectors before that. That's the idea of residual. Yeah. So once this is done, the final thing is to have a linear layer here. Let me just combine them both. Here there is a linear plus softmax, and this will give us a y. So this is what a transformer architecture is. Now, this is just the bare bone architecture. One can have multiple multi-head attention blocks, and then they can have multiple fully connected layers, and you can repeat those blocks multiple times and so on. This is a bare bone architecture of how a typical transformer works.